Great. Okay. So, as I said, we had our first presentations on Egyptian and Babylonian math. And so I wanted to go over a few interesting things about them. That actually, I find them really interesting. So as was mentioned in the presentations, Egyptian math has got very few original primary sources. And so there's a few things that are on stone, so that's something that's going to endure. But really, if you're looking for mathematical texts, since they wrote on papyrus, you can imagine that's kind of fragile. And so there's really only two mathematical texts which survived. The most famous of which is the Rhind papyrus. Rhind was a Scottish antiquarian. Is that I'm saying that right? Someone who studied antiquities, anyway. And it's now in the British Museum. So this is what is actually on the papyrus. It's written in hieratic, which is kind of like the cursive form of hieroglyphics. And so if you convert it to hieroglyphics, you get this thing here. And those who saw the presentations already can recognize some numbers. Hopefully you can see numbers. So for example, this, it represents a 4, and there's a mouth over it. So that actually represents the fraction a quarter. That represents the fraction a seventh. There's 1, there's 2, there's 8. Can anyone see a 10 somewhere? Oh, there we go. There's a 10 there. So this thing here is a symbol for 16. Okay, and so if we translate it, we get this sort of translation. A quantity, so as we already noted, Egyptians, when they did fractions, really only dealt in unit fractions. And this was just kind of belief that there was, or, just the way they thought, a thing that there was only one part. So when you say a seventh, a third, a fifth or whatever, it didn't make sense to them to talk about 2/7 or 3/7 because there's only one 1/7. That's the unique seventh fraction. And so when you see Egyptian arithmetic, it can get incredibly complicated for the simple fact that they have to put everything as unit fractions. And so, for example, if you were to figure out what the area of a circle of diameter 10 would be, the first thing they would do is remove 1/9 of 10. And so that obviously is going to be 9. Hang on. So you remove 1/9. So that's 10/9. So you're going to get 8 and 8/9. Well, they've got to write 8/9 as a whole bunch of distinct unit fractions. And so that adds like this whole layer of complexity to the problem, which you'll find in the homework. There's some of those things you have to do. Okay, so here is a problem. A quantity, a seventh of it added to it becomes 19. Okay, so in modern terms, that would be 1 plus 1/7 times x equals 19, which is obviously, x is obviously 19 divided by 1 1/7, and then we would do fractions and get an answer pretty easily. Okay, here's how the Egyptians did it. They used this method of solving equations like this, the method of false position. Has anyone ever seen that before? Okay, so you start off by assuming an answer, by assuming something easy as the answer. And so, for example, they assume that the quantity is 7. That's an easy number, right? Because it's easy to compute 1/7 of 7. And so 1/7 of 7, of course, is 1. And so that's their first approximation to the answer is 8. But 8 is obviously wrong, right? So what they're going to do is then they're going to multiply 8 by a number to get it to they're going to multiply 8 by some factor to get to 19. And when they figure out what that factor is, they then multiply that by 7 and they've got the answer. Does that make sense? It only works because we're dealing with linear relations here. Okay, this is this mode. So you start off with 8. Okay, we double 8 to get 16. We halve 8, we get 4. We take a quarter of 8, we get 2. We take an eighth of 8, we get 1. Okay, now they've got to look for 19. They've got 19, right? 19 is 16 plus 2 plus 1. Okay, so that means, so they check off 2, a quarter, and an eighth. And so that means that is their 1/7. That's their blowing up quantity. Okay, and then to double check it, right? So this is just double checking that they've got the answer. So they take their answer, they double it and quadruple it, and you add it all up together, and you get the quantity. A 7th is this. Add it all up, it's 19. It works. Okay? So, this is incredibly complicated for what we think is a very straightforward problem, right? And I like to illustrate this because it kind of shows how cool the Islamic mathematicians were with their algorithms for doing multiplication, but with doing arithmetic, which is kind of like the way that we do things. We can see that's really kind of straightforward. If you have a messed up way of doing things, then your algorithms have to be messed up and have to be much more complicated. So this is this method of false position, which is an old method. It was used quite extensively for quite a while. Anyone got any questions about this problem? Okay. So, as I said, Egyptian fractions, they had to use unit fractions. So actually nowadays there's a branch of recreational mathematics called Egyptian fractions. So it's kind of like Sudoku puzzle working with Egyptian fractions. But if you look at the Rhiine Papyrus, they give like kind of like tables where they say, you know, what is 2/11 would be, or 2 divided by 11 is actually 1/6 plus 1/66. 2 divided by 13 is 1/8 plus 1/52 plus 1/104. Here's 2/23. So let's actually do an example. So how would we get 2/13? So what would we do? We'd start off with, well, if 1 is 13, then we'd kind of halve it, and we'd get 6.5. We quarter it, and we'd get 3.25. And if we halve it again, we get 1.5 and an 8. Now, what are we looking for? what we want on this column here is 2, right? So once we get 2, then we would solve the problem. So we see that we've got a start. We're kind of going towards 2 here, right? So what we need, well, what do we need? What are we missing? So what added to this makes 2? Like? 3/8, except you're not thinking like an Egyptian. How would an Egyptian think of 3/8? 1/8 and a quarter. Okay, so now we've got to somehow find a quarter and an eighth. Okay, if we look at this, it gives us a chance to find a quarter. So how do we change this to a quarter? What have we got to divide by to get a quarter? How many quarters in 3 1/4? 13, okay. So let's divide a quarter by 13, and so that gives us 52, and the answer is a quarter. What are we missing? We're missing an eighth. Okay, how do we get from this to an eighth? We divide by 2, and it's 104, and voila. Here is our thing, because this plus this plus this is 2, right? Remember, 13 is 1. So here we get 2. So this is, if this is 13, and we've got 2 here, this is 2 divided by 13. And so 2 divided by 13 is 1/8 plus 1/52 plus 1/104. Okay? So it kind of is like a Sudoku puzzle. I mean, it's not really an algorithm, right? You've really got to think of things. You've got to think, well, what could work? You've got to look for patterns. You've got to look for certain numbers, and then you work from there. So kind of interesting. Here's a geometry problem from problem 48. Again, here is the erratic, and here it is put into hieroglyphics. Again, we can see plenty of numbers. So what is the problem? Compare the area of a circle and of its circumscribing square. Okay? Square of side 9, that's an easy one. Okay? So one thing you should have noted already, if you'd watched the videos, and just by what I'm speaking, is the basic Egyptian way of doing things is doubling and halving. Okay, so this is how they do a square, you know. So to do 9 squared, you've got to do 9 by 9. So you start off with 9. So Sitaf is just a unit of length. So we double it, 18, quadruple it, 36, times it by 8 to get 72. And so to get 9 times 9, you do 1 and you do 8. 1 plus 8 is 9. So therefore we add the 9 to the 72 and we get 81. So the rule for a circle of diameter whatever is to take 8/9 of the diameter. It is this, the area of a circle is approximated by the area of the square of side 8/9 of the diameter. So who did Egyptian geometry? So this means that they're doing some approximation for pi, right?
Mm-hmm.
Yeah. And you can actually kind of figure out what it is. But so 8/9 of 9 is 8. Squaring it, well, you've got to just double it, quadruple it, multiply it by 8. That's it. You don't have to do anything else. This is 8 times 8 is 64. So the diameter, a circle of diameter 9 to the square of psi 9 is 64 to 81. And you can go ahead and you can figure out what that approximation for pi. Do you remember what it was?
3.16.
3.16. Okay. So.
Okay, so you have a circle of diameter 9, and then, but on your first line below it, you have 8.
8, right. So the rule is that a circle of diameter 9 has the same area of a square of side 8. So you take the diameter, multiply it by 8/9, and you square that. Okay. So so the area equals 8/9 of the diameter squared. Right? Whereas in real life, what is it? It's actually pi on 4, isn't it? Diameter squared. That makes sense? Right, because the diameter is twice the radius. Twice the radius squared is 4r squared. The 4's cancel, you get pi r squared. Right. So that means pi on 4 is approximated by 64 on 81. So this ratio here is approximation for pi on 4. Okay, let's talk about some Babylonian mathematics now. And by Babylonian, we're really talking about, like, if you saw the presentation, it's, you know, include the Assyrians, the Kassites. There's a whole bunch of empires, one replacing the other. So of course, an important thing if we're talking about history, okay, so if we're talking about Egypt, we're really talking about the Nile River. I mean, this is why we had civilization in Egypt very early on. The Nile River is incredibly fertile, and it does this thing that every year it floods. I think it's sometime around March or April. And it always floods at the same time that Sirius, the star, is in some certain position. So that's why Sirius was very important to the Egyptians. But the floods were not devastating floods. You know, the Nile would sort of overflow its banks, cover the land, and then later on in the year it would sort of go back down, and it would just completely replace the soil with this really rich black soil. And so the Egyptians were able to get kind of like 2 crops in the season. So that made them, you know, they had a lot of agricultural wealth, and that led to the, you know, the civilizations and that. And so their whole way of being is governed by the Nile. You go to Mesopotamia. Oh, and so Egypt, if you think about it, is really isolated from the rest of the world, because it's got deserts, the sea. So it's kind of like a natural country, so a natural land. And throughout its history, you know, there was an upper Nile and a lower Nile. And sometimes the kingdoms would be different, and every now and again there'd be someone powerful who'd unite the whole country. In Mesopotamia, it's a little bit different. There you've got the Tigris and the Euphrates, again 2 mighty rivers, and they would flood as well, but not like the Nile. The Nile was good to the Egyptians, while the Tigris and Euphrates were not so good. So the floods there are much more devastating. There's kind of mountains to the north, and so the kind of floods they'd get these flash floods coming down from the mountains, destroying lots of things. And so Mesopotamian religion was kind of like much more, you know, the gods live up high and they wreak vengeance on us, sort of thing. There's no stone there, so they do everything with clay. They made their buildings out of clay, and they also made clay tablets. And they had this type of writing called cuneiform, where the clay, you'd have a clay tablet which kind of fit in your hand. You have a stylus where you sort of poke marks into the clay, creating these kind of marks here. And so here is, so whenever you see, and of course being clay, afterwards they let it dry in the sun, and so clay tablets get preserved. And so there's like 1 million clay tablets have been found. And they're all around the world, and they have, if you look at their number, you can kind of figure out where they are. So if you see YBC, you know it comes from Yale. If you see BM, it's the British Museum. If you see Plimpton, it's Columbia University. It was a big thing to get these tablets, and they do these excavations, particularly, at the beginning of the 19th century through until the beginning of the 20th century. There's huge excavations where they just dug up tons of these things. Okay, and I don't really know the story of how it got translated, but since the early 19th century, we've been able to read these inscriptions, so I don't know where that comes from. But anyway, here is some Babylonian for you. Ma, na, sa, na, and ma, sa, na. I don't know. Looks like a strange language to me. But anyway, so these types of tablets, a lot of them they found were scribe. It's for teaching scribes. So if you were a scribe, you needed to know how to do arithmetic. And so this tablet here is a translation. I found a stone but did not weigh it. After I weighed out 6 times its weight and added 2 jin and added 1/3 of 1/7 multiplied by 24, I weighed it 1 mana. What was the original weight of the stone? The original weight of the stone was 4 1/3 jin. This is like terrible algebra problems, right? Because, okay, so we want to find, so why we would think about it, we want to find x, but we don't find x exactly. What we did was we weighed 6 times x plus 2. And then we added 1/3 times 1/7 multiplied 24 of this quantity. I got the answer 1 mana. I think that if I remember right, there's 60 jin in a mana, so everything is base 60. Okay, and then it gives the solution to this. And so then you see the next problem. I found a stone that did not weigh it. I weighed 8 times its weight and added 3. So if you look at this from a pedagogical point of view, maybe the pre-MA students here would say this is not that great. But anyway, well, here's a subtraction one. I found a stone but did not weigh it. After I subtracted 1/6 and added 1/3 of 1/8, I weighed it 1 mana. So here we go. One answers 1 mana, 9 jin, and then there's 60 C in a jin. So they could do linear equations quite easily. So just a normal scribe would be expected to know this. Here is a more interesting problem. This is a quadratic problem. The igibum exceeded the igum by 7. What are the igibum and the igum? Okay, so the first thing you got to know is, well, what the hell is an igibum and what is an igum? An igibum and igum are two numbers. They're basically reciprocals of each other. So that the igibum times the igum is 60. Remember, 60 is 1, 0. So, 610. But they were remember, they were very loose with their units and that. So, 6 could refer to 6, or it could also refer to 1/10, or it could refer to 1/360th. So they were very loose with where their unit was. Okay. So what we've got here are two numbers such that x times y is, in our terms, is 60, and x minus y is 7. Okay, so hopefully all of you recognize that this is a quadratic problem, right? Because you replace y plus x plus 7, so you get x times x plus 7 equals 60. So you get x squared plus 7x minus 60 equals 0. So it's a quadratic equation, and so we would solve it with the quadratic formula. And that's what the Babylonians did, except they didn't have formulas. So how do you prove something if you don't have how do you find something if you don't have a formula? You have a recipe, and the recipe turns out to be the same as the formula. Of course, since it's a recipe, you've got to have different recipes for different cases. So depending upon the sign of the coefficients, you have a different recipe. Some places you add, some places you subtract. So let's have a look at this. As for you, halve 7, by which the igibum exceeded the igum. So you see that this is practically a formula right here. So why are we halving 7? Well, we're halving 7 because that's this minus that. And 330, 3.5. Right? Multiply together 330 with 330 and 1215. So 3.5 squared is 49 on 4, which is 12.25. Right there. To 1215, which resulted for you, add 1 0 the product, and that's what you get. You get 72.25. What is the square root of that? It's 830. Lay down 830 and 830. It's equal. And then subtract 330, the Tackleton. I believe Tackleton we would translate as semi-difference. So the Babylonians were really into taking averages. So if you gave them two numbers, they liked doing that. That was kind of like a basic arithmetic procedure for them. So you subtract 330, the Tackleton from the 1, and then reverse, that means you turn over the tablet, add to the other. 1 is 12, the other 5. 12 is the igibum, 5 is the igum. And sure enough, 12 times 5 is 60, 12 minus 5 is 7. Okay. And so if you actually go through this and turn all the written instructions into formula, you would get, what would you get? You would get 7 on 7 plus or minus square root of, what was it? 7 squared minus 4 times 60 is 240, divided by 2. But if we take the 2 and we put it in to the numerator, we get 7 on 2. If we now put the 2 inside the square root, that's like dividing by 4. We get 7 on 2 squared. And that 4 goes away and we get 60. Right? And you see that, did I do, oh, did I add it, don't I? Yes, because it add 1, 0, the product. So you see they've taken the 7, they've halved it, they've squared it, added the product, taken the square root, and they plus and minus that from the 7 over 2. So this is exactly the quadratic formula. Okay, so scribes were expected, just as part of normal mathematical education, to be able to solve linear equations and quadratic equations. This is another interesting tablet. So it shows a square, and it shows here 30, and here is the diagonal. If that is 30, then the diagonal is 42, 25, 35. And they got that because they multiplied 30 by 1, 24, 51, 10 to get that answer. What is this number here? What's 1, 24, 51? So what do you multiply the side by to get the diagonal? Root 2. Yep. So that's actually a pretty good approximation of root 2. So how would they go about finding root 2? So let me go to the whiteboard, show you how that might have been done. So let's say you're trying to approximate root 2. So one approximation might be 3 halves, and another might be 4 thirds. Okay, they're pretty, when you square them, you get pretty close to 2. In fact, I would say that each one is as good an approximation as the other was root 2. And the reason for that is, what happens if you multiply 3 halves by 4 thirds? You get 2. Okay? So however much this is off, 3 halves is off by root 2, 4 thirds is off by a similar amount. And in fact, one's an overestimate and one's an underestimate. And how would you make a better estimate? If you know that the true answer lies between that, what would you do? Take the average. Like I said before, it's a basic arithmetic operation for them. And so if you take the average, that is what, 17 on 12, which is 125. Okay, and so, well, we can come up with another one just as good by multiplying the reciprocal of that by 2. So if we look at 2417, that's another approximation of root 2, just as good, because when I multiply that by that, I get 2. So I can go ahead and take the average of that. And if I took the average of that, I believe I get some number like 12411. And then if you do that again, you get 12410. And so this is probably how they got their approximation for root 2. And you can see that It's actually a pretty nice method. It's much easier than the way we saw before of taking roots by doing that arithmetic way. This actually converges really, really quickly. Basically, every time you do one step, you double the number of places of accuracy you get. So actually, not only do you get 12411, but you actually get it to like, I think, 3 more places of accuracy. It actually turns out to be the same as Newton's method, if anyone remembers Newton's method. Does anyone do Newton's method in calc any day nowadays? Maybe?
No.
Yeah. So if you look at it, you can actually turn it into Newton's method. Not that they knew Newton's method, and they didn't do it by Newton, but they did it by this process of averaging. But that's why it turns out to be such a good method. Okay. So I want to finish up by just looking. Oh.
So you're not sharing the screen, by the way. For the Zoom.
It's not showing the screen? Oh, thank you. Oops, I did something wrong here. Usually if you press escape, that works. Zoom, share screen. Okay, thanks, Izzy. So the tablets we saw before were all kind of boring ones, just kind of like schoolwork sort of thing. But they do exist some really interesting tablets. So if you look at the presentation, Junyan talked about Plimpton 322, which is the Mona Lisa of Babylonian tablets. It gives a table of Pythagorean triples, but the order in which they get it is in descending order of kind of ratios. So it kind of looks like of ratios of, side to hypotenuse. And so it kind of looks like that it could be considered a trig table, which is really amazing because that's like thousands of years before trig was invented. So it's an early evidence. So it might not be exactly trig, it might just be used for solving triangles, but it's still an amazing tablet. Here's another amazing tablet. Here's a labyrinth. So labyrinths in ancient times were thought of as really amazing things. They thought they had all kinds of amazing properties. And so here is a tablet which has a labyrinth on it, and it's fairly straightforward to figure out how they actually constructed the labyrinth. So it's sort of they constructed outside going in. So you have the black and red is just for our convenience. You put those in first. So we have 2 open gates here and a closed gate here. And then you sort of work in, you sort of alternate between black and red. And here in steps 7 and 8, they change direction somehow, kind of block it off, and they just keep on going. And so it's fairly straightforward to see how they actually constructed this labyrinth. Here is an amazing tablet, and on it is written this number here, which is approximately 10 to the 26, which is, I don't know, past septillions and octillions, do that. You say, well, what is this number? Why would they be interested in such a big number? It actually turns out to be 20 to the power 20, which is just kind of mind-boggling that someone 4,000 years ago figured out what 20 to the power 20 is. And I just think that just means that there were math nerds 4,000 years ago. I think that's the only explanation. There can be no practical reason whatsoever for someone to figure out 20 to the 20. It was just someone kind of showing off or doing something. I don't know. It's pretty amazing. And so you can just kind of make out the figures there. This is kind of like a 10 and 3 downward strokes. So hopefully you can see that as read that as a 13. They also did some kind of non-standard things. So like most of the things, the problems that you see in the scribe tablets are kind of nice, use nice sexagesimal numbers, right? So base 60. So you can do anything with 2s and 3s and 5s. So they did very rarely with 7s and 11s and 13s. But there are examples, rare examples of them using these non-sexagesimal numbers. So here is 1, 1, 1, 1 divided by 13. 1, 1, 1 divided by 13. 4, 4, 13, 7. You get the answer there. And this is the most amazing tableau. So MS, which I believe is in Stockholm, I believe this is the library there in Stockholm collection there. So this is a tablet computing the weight of a giant icosahedron. Now, how could that be? Well, because obviously, you know, they don't have a Babylonian word for icosahedron or whatever. And so when they translate the text, it's asking to compute the area of a horn figure composed of 6 minus 1 times 4 gaming piece fields, where each piece has area given by that, and the side is S is 3 cubits. You remember a cubit is kind of the length from your elbow to the tip of your finger. It's like 1.5 foot. So what does this mean? So a gaming piece field, they know in Babylonian terms, means an equilateral triangle. And they give the area as a half S squared root 3 on 2. If you actually figure it out, if you have an equilateral triangle of side S, this is actually the formula for the area of an equilateral triangle. They used an approximation for root 3. And so they compute this area of 20 equilateral triangles. They then compute the volume of that, assuming that it's an area and it's like it's 1 finger thick. And then they compute the weight of such a figure made of copper, knowing that a copper square with side 1 cubit and 1 finger thick weighs a talent, which is around 30 kilograms. And so what do you use 20 equilateral triangles for? You make 20 equilateral triangles, so they conjecture with 20 equilateral triangles, you make a icosahedron. And then when they talk about the horn figure, they're thinking of this kind of shape. So this is the standard way in which icosahedron is made. you get this, and then you fold it up and you fold it into a icosahedron. And the fact is they did 20 as 6 minus 1 times 4. And it's easy to see this as 6 minus 1 times 4, right? Because you've got a hexagon here. You take the 6 side, you subtract 1, and for each side, you sort of go out 4 triangles. So that's a standard way in which to count the size of a icosahedron. It's so big. It's a icosahedron whose sides are 4.5 feet. Right? And when they go ahead and figure out the weight, it's 1/1845 talents. That's like 2.5 tons. So it's really kind of amazing evidence that the Babylonians were really good at math, really. So